Pay attention, everybody. We're going to start off by looking at examples of how Rolle's theorem and the mean value theorem work, okay, from the homework. Then we're going to look at, okay guys, we're going to look at, we're going to revisit very quickly first derivative and second derivative tests, okay. I know I mentioned them yesterday, but we'll go over them formally today. They take about a total of 3 minutes to get fully. And as I had students come in and do work over homework with me earlier, and they honestly were shocked because they were like, this is, because they thought they were doing something wrong, because they're just like, this, it can't be this easy. Well, it's literally that easy. Okay, so, but let's first start off with talking about mean value theorem and Rolle's theorem, okay? I've got problems in the homework that we're going to go ahead and look at. These problems, I've selected them already because I know they're just going to be good problems to go over, okay? So, the first set of problems has to do with Rolle's theorem, okay? Our first one here, okay, the Rolle's theorem problems. A lot of times when you have a problem, when you're asked to do something involving Rolle's theorem or the mean value theorem, a lot of the time you're explaining why something comes out the way it is. So it's not necessarily a, I'm finding a numerical answer. I'm showing or explaining why this must be the case, okay? So for our first problem here, number 7, okay, we've got the function f of x is equal to x times root x plus 4, okay? All right, and we're asked to find the two x-intercepts of the function f, and then show then that f prime of x must be equal to 0 at some point between the two x-intercepts. Okay? But just basically saying use Rolle's theorem to explain why there must be a critical point in between our two x-intercepts. Okay? Now, first thing we got to do here is figure out the x-intercepts of this thing are. Before I even do that, I want to go ahead and say what the function's domain should be. Why do you think that's going to be the case?
Find the maximums and minimums.
No. What's important about Rolle's theorem and the mean value theorem?
Between 2 points.
Besides being between 2 points, what's one condition for both to work? The function has to be what?
Continuous.
Not just continuous, but differentiable. Okay? So I want to check the domain to make sure the thing doesn't have any gaps or holes. Okay, because that will help me. And in this case here, if there's no gaps or holes between my two x-intercepts, the thing should be differentiable between the two. Okay? Should be, because there's nothing weird going on here with absolute values or anything crazy like that. Okay? So, what's this thing's domain going to be?
Greater than or equal to 1.
Is it 1?
Or 0.
All x.
Negative 4.
Negative 4.
Oh, yeah.
Negative 4 is the point that would make this equal to 0. So my domain should be all x greater than or equal to negative 4. Okay? Every other, all the x's above negative 4 work just fine. All the x's below negative 4
Undefined.
would make this thing undefined. Okay? So that's going to be my domain there. Okay? Now let's find the x-intercepts. And guess what? By finding the domain, guess what I found? An x-intercept. What are the x-intercepts? If I make this minus 4, the inside of that square root becomes 0, right? The square root of 0 is 0, which leaves the whole thing being equal to 0, right? So one x-intercept happens at minus 4. Where's the other one going to occur?
0.
0, because of that for an x. Okay. So my x-intercepts are at minus 4 and 0. So the interval I'm looking at here, I'm looking for my open interval. In question is going to be from minus 4 to 0. Is that within the domain?
Yep.
Yes, it is. Okay? This works in the domain. So then, all the conditions of Rolle's theorem are met. Okay? I've got 2 points that are equal to each other. In this case, they're x-intercepts. So they're both equal to 0. F of negative 4 is 0 and f of 0 is 0, which is fine. And I've got an open interval in which the function is differentiable on. Okay? So from that, by Rolle's theorem, okay, there exists sum x within the open interval from -4 to 0, where f prime of x is equal to 0. And if you want to be really spiffy with this, you could throw in an explanation because f of -4 is equal to f of 0, and the function is differentiable between -4 and 0. Okay, but that's just that's basically just what Rolle's theorem says.
What was it? By Rolle's theorem, time.
There exists
Do we have
there
to say
exists
open?
some x. Uh-huh.
Do we have to say open interval?
Oh, right there.
Yeah.
I just put it there so you understood this is not the ordered pair -4, 0, but the open interval -4, 0. Just the notation's the same. Okay.
So that's not an ordered pair then.
No, it's not an ordered pair. That's an open interval from -4 to 0. That's the notation for it. Okay.
Okay.
All right. Now, there's another way I could have handled this number 7. What else could I have done? It's asking for a derivative, right? Equal to 0.
Yeah.
So what can I actually do?
Find the derivative.
Find the derivative and set it equal to 0, right? There's nothing to prevent me from doing that. Okay. Let's go ahead and take a look at what that looks like. F prime of x should be equal to what rule would I use on this?
Product.
Product rule. And when I hit this guy, it's a product rule and with a what inside of it? What rule?
Oh, chain rule.
Chain rule, there we go. So the product rule says keep first one the same, multiply it by the derivative of the second one, so that should be 1/2 x plus 4 to the negative 1/2. Okay. Then
Times 1.
times 1, but there. Okay. Then we keep that one the same and multiply it by the, then we add to it derivative of the first one times the second one kept the same. And I know it's getting squished there to 1/4, like that there, okay? We set the whole thing equal to 0. And when I set it equal to 0, I'm going to clean it up a bit. This here will clean up to be x over 2 times x plus 4 to the 1/2 plus x plus 4 to the 1/2, okay? I'm going to go ahead and move the x plus 4 to 1x plus 4 to 1/2 over on the other side, yes?
What is after x plus 4? 1?
There's a 1/2. It's just the 1/2.
No, but under the 1/2.
Right there?
No. That's the, on the first x plus 4.
X plus 4 to the negative 1/2 times 1.
Plus 1 times.
Plus 1 times x plus 4 to the 1/2.
Oh,
Okay. Alright. This looks like it might be hard to do. Resist the urge to get a common denominator there. Instead, I can use a sneaky trick. I can move this one over here as minus x plus 4 to the 1/2 equals x over 2 times x plus 4 to the 1/2. Those are the same thing, right?
Multiply.
So I could cross multiply and get rid of it. So it should be minus 2 times x plus 4 is equal to x. So minus 2x minus 8 is equal to x, which means minus 8 is equal to 3x. So x is equal to negative 8/3. Is negative 8/3 between negative 4 and 0?
Yeah.
Yes. So we just confirmed then that the derivative does, that the critical point does exist at negative 8/3.
Wait, I'm confused on your math. When you cross multiply.
Okay. These are the two same things, right? Both to the 1/2. So what happens when I multiply, when I square root? Square roots go away, right? 1/2 plus 1/2 is 1, so it goes away. That's all I did.
Okay.
And that 2 just goes along for the ride. Just how I end up, when I cross multiply, that's how I end up with minus
X
2.
plus
Oh,
2x.
Okay. Like that there, okay? Now, you might say, well, Mr. Dowell, if I can do that every time, why do I need to bother with Rolle's theorem? It's because there are functions out there which are would be way too difficult to do this process to, okay? But if I can find my x-intercepts, or if I can find 2 points where they're equal, I can confirm the existence of the critical point using just Rolle's theorem, okay? So also too, note this was way faster ultimately than taking the derivative each time, okay? And so if I'm just being asked to confirm the existence of a critical point, but not actually find the critical point, just use Rolle's theorem, okay? It comes out fast every time, okay? Let's look at 2 more Rolle's theorem problems, okay? And we won't do, the book will ask you to do them completely. We're just going to do the Rolle's theorem part. So the book would ask you to do the same thing I just did up there. Instead, for time's sake, I'm just going to use Rolle's theorem on both, okay? So, we've got 13, which is f of x is equal to x minus 1, x minus 2, x minus 3. And we're looking at this thing from 1
A good time, Belly.
to 3. Okay? So, first and foremost, what type of function is this ultimately? It's a what? Polynomial. Polynomials, by definition, are always differentiable. Okay? So I don't even need to bother with that. We know it's differentiable as a polynomial. Okay? Next, we just need to figure out what the zeros are, right?
3, 2, 1.
They're happening at 3, 2, 1. So f of 1 is equal to f of 3, isn't it? Okay? So I know f of x is differentiable.
What does differentiable mean?
You can take the derivative
Okay.
for anywhere. Basically, it's it means you can take the derivative on the interval in question. Okay. Differentiability also directly implies continuity. So if something's differentiable, it's automatically continuous. Okay. The other way around is not true. So something that's continuous is not automatically differentiable, but almost all the functions we see are differentiable because, let's face it, this is calculus class, and we want to take the derivative, don't we? Okay. So a lot of things we see are differentiable. But anyway, f of x is differentiable. F of 1 is indeed equal to f of 3, right? So therefore, by Rolle's theorem, a critical point exists on interval from 1 to 3. On that. That's it. That's all I had to do. Okay? Was that hard?
No.
No. Just use my words. Actually, too, I can take this a step further and show there should be at least 2 critical points. Because what's also equal to this? F of 2. So between f of 1 and f of 2 there should be a critical point, and between f of 2 and f of 3 there should be a critical point. Again, using Rolle's theorem. Okay? But we didn't need to do that. You just needed to confirm the existence of a critical point on 1 and 3, and that's what we did. Okay? Because f of x is differentiable, f of 1 is equal to f of 3, so Rolle's theorem applies. Okay? Any questions? Yeah, Rolle's theorem is pretty much essential. Okay. Let's see. Let's look at another one. Let's look at, we're going to move on from the Rolle's theorems questions because they're fairly straightforward at this point. You should get how they work. Well, let's look at some mean value theorem questions.
What was that I'm sorry, what was that there for by Rolle's theorem?
By Rolle's theorem, there's a critical point on the interval from 3 to 1.
Okay.
Yep.
Thanks.
Which is what Rolle's theorem basically says. It's asking, is there a critical point here? If it applies, then the answer is yes. If it doesn't apply, then the answer is we don't know. No, it's not that it doesn't exist. It's just that we don't know. Okay, that's another big thing, guys. Okay, if Rolle's theorem does not apply, it's possible for there still to be critical points. It just means we have a situation where Rolle's theorem doesn't work for us. Okay, you'd have to find the critical points using some other method. Okay, they could very well exist still. They just might not. There might be some problem, like the interval might have a hole in it somewhere, or the endpoints aren't equal to each other, or something like that, okay? Just means we can't use Rolle's theorem to confirm it, okay? Well, let's take a look though at mean value theorem. So remember, these are mean value theorem problems. The mean value theorem works very similarly to Rolle's theorem, so it has the same test. You want to check to see if the function is differentiable on the interval given. Okay. The first main difference is you're checking to make sure that the endpoints are not equal. Okay. That is, f of a does not equal f of b for Rolle's theorem. For the mean value theorem. Okay. Then what you are going to do is you're going to take the derivative and set it equal to basically the average rate of change, or the slope between our 2 points, endpoints in question. Okay, and then solve it that way. So let's take a look at an example of this. This is 39. Okay, we're going to apply Rolle's theorem, apply the mean value theorem. I keep saying Rolle's theorem. Apply the mean value theorem on f of x equals x squared from -2 to 1. Quick question for you all. Okay, first test, is that thing differentiable?
Yes.
Yes. So f of x is differentiable.
On the interval.
Yeah, differential.
How do you know if it's not different?
There's a hole, or a gap, or an asymptote on the interval, or you have a absolute value function,
So
something like that.
So, okay. So you couldn't do like the question rule to that if something's not differentiable? Would it not work?
Not necessarily. So for example, if this was 1 over x squared, there'd be an asymptote at 0, right?
Yeah.
And therefore it's not differentiable between -2 and 1, because at 0 the thing's undefined.
But I could take the derivative.
You can take the derivative, yes, but the derivative doesn't exist at 0. You would take the derivative, evaluate it at 0, and get a whole
It's
big
just
block
not,
of
it's just not
undefined.
continuous.
So it's not continuous.
Okay.
If it's not continuous, it can't be differentiable.
Okay.
But this one is, okay? So f of x is differentiable, that's what we need to test. Now we need to see, is f of -2 not equal f of 1? What's f of -2 going to be? 4. What's f of 1 going to be? 1. They're not equal to each other, right?
True.
So that means I can use the mean value theorem. So the mean value theorem says then that f prime of x is going to be equal to, or f prime is, there will be some point c, let me rephrase it, means there exists a point c such that f prime of c is equal to f of -2 minus f of 1 all over -2 minus 1, okay? That's what it says, okay? So, let's work this out real fast. What's the derivative of x squared?
2x.
2x. So that means 2x has to be equal to this thing evaluated out. So it should be 4 minus 1 over -2 minus 1. So 2x is going to be equal to 3 over -3. So 2x should be equal to -1. That means x is equal to what? -1/2. So,
That dead spot.
I hate it. This is the value of x,
At C. Or at.
of x at c, or that satisfies the mean value theorem. So basically, the derivative at -1/2 is the same as the slope of the tangent line, or the secant line, excuse me, between -2 and 1. That's what the mean value theorem says. Okay.
Would we have to write that out there?
We could just end it at x equals -1.
Yeah, you could just leave it as x equal -1/2. That's fine. That's what we're usually after. I wrote up the words just as a, just so you understand what we've actually found here. Okay. All right. So that's the mean value theorem. Okay. And that's how it works. Is that truly difficult? It's not too bad, is it? Okay. You're taking a derivative and you're setting it equal to a regular slope. Okay. And you're just figuring out what x is from there. All right. Shouldn't be too terrible. All right. One more of these before we move on. Okay. Let's look at. We're going to look at number 44 here.
Before you move on.
Paid to be in that one.
Okay.
Bigger money.
We're going to look at one more. Number 44.
A chance.
I'm going to play with the camera. For those of you watching at home, well.
Alright, you're good.
All right.
There's only a game ahead of me.
Good. 44. For 44, we've got f of x is equal to x plus 1 over x from -1 to 2. And we're applying again, we want to see if the mean value, what the mean value theorem tells us. Okay? Well, can I even use the mean value theorem here?
Isn't there a hole?
Ah, there's a hole, right? Or specifically an asymptote. Where is it located? At 0. So, at 0, this thing is not differentiable, is it? So, we would say not differentiable everywhere. Oops, not everywhere. On -1 to 2. So, the mean value theorem doesn't apply. Okay? And that's it. That's all you have to say. You can't do anything. Okay? Because it's not differentiable. Okay? By the way, unlike Rolle's theorem, okay, usually if the mean value theorem doesn't apply, it means the thing doesn't have a point in between where the slope of where the derivative is equal to the slope of the secant line. Okay? So with Rolle's theorem, you can have Rolle's theorem not work and still have a critical point. But the mean value theorem doesn't work. That typically means that there is no point in question. It's just not going to happen. Okay? And if I were to actually graph the system out and try to find that point, you would discover it doesn't exist. Okay? Yeah?
If this was x squared plus x over x, would it be differentiable?
X squared plus x over x. There'd still be a hole. And the hole makes it so it's not differentiable.
I'm just
Okay.
asking.
Yep. Yeah, you can still have, that hole would mean you're still got a discontinuity there. Okay? And you can't do the derivative at discontinuity. Okay. So, any questions about mean value theorem or anything like this right here? Alright, good. We're going to move on. Okay? Now, we're going to do probably the 2 easiest things that we'll ever cover all year. Okay? They're super easy, okay? This falls under the heading of analyzing a graph
Less than 5
using the
minutes.
derivative. Sorry?
Less than 5 minutes.
Less than 5 minutes, okay. So, analyzing a graph using the derivative. Okay? So we've already figured out how to find critical points using the derivative, right? Critical points are going to be maximums or minimums or saddle points, okay, of your graph. Turns out I could also use the derivative to tell when a graph is increasing, decreasing, or constant. Okay?
True.
It's called the first derivative test. Okay? First derivative test. And what it says is the following. If f prime of x is greater than 0, then f of x is increasing. Okay? If f prime of x is less than 0, then f of x is decreasing. And finally, if f prime of x is equal to 0, then f of x is what?
Constant.
Constant. Done. First derivative test. That's it.
So are you.
That's all there is to it.
Hit it.
Okay? I mean, it's literally that obvious. Okay? Now, what is something as easy to accomplish for you? This can help you when you're doing, it just confirms things you know from sign analysis, for like finding like maximums or minimums and things like that. The other big thing this lets you do though, is this really comes into play when you're looking at graphs and you don't have the equation. Okay? So an example of what I mean, I'll give you guys a second to finish copying it down. First derivative test. Okay?
Oh, you remember that time we did graph?
But if we looked at a graph of something, I could from that graph tell what the derivative should look like, or what the original function should look like. So an example of that might be, example graph. Okay, so if the following graph is f prime of x, so this is a graph of the derivative. Okay. From this graph here, I can tell you the intervals on where f of x is increasing and decreasing. I can also tell you where the critical points are. Okay? So f of x from this graph is increasing on -3 to 2. Why? Because that's where this graph of f prime of x is greater than 0. Right? Okay? F of x is decreasing on, from where to where? -infinity to -3, and 2 to positive infinity, because that's where f prime of x is less than 0. Okay? Okay? And lastly, where does this thing have maximums and minimums? At -3 and 2. -3 being a minimum, 2 being a maximum. Okay? And so from that, I can actually go through now and do a rough sketch of what f of x should look like based off this graph here. Okay? Now, it's a rough sketch. I'm not going to get everything correct, am I? Okay? Mainly because I lack things like the derivatives doesn't tell me, for example, where the y-intercept is. It doesn't tell me, precise y locations of where my graph is. But it does tell me where the graph changed directions and when it's going up and when it's going down. Okay? And if I played around with it some more, I could figure out, basically about how far certain things should be above other certain things and things like that. Okay? But from this, I could get a basic graph. And so my basic graph for this thing should look like this. It should be something like, okay, this is -3, okay, 2. So f of x should look like,
When you finish with this, can you scroll back up?
should look like that right there. Okay? Again, not the precise picture of what f of x is, but the basic picture of what it should look like. Correct? Okay. And it should look like that. Can I stop right here?
Yeah.
Should look like that based on everything I figured out about f of x from the first derivative test. And that's where the first derivative test is really useful. Okay? Yeah? Yes, you may go use the restroom. Okay? Any questions about the first derivative test at this point?
What's the U mean? I always forget.
Oh, and?
Yeah.
It means union specifically. Okay? Means both those sets are sets where this thing is decreasing.
How'd you know there's a minimum at x equals 3?
Oh, minimums occur when I go from negative slope to positive slope, right?
Oh, yeah.
So I'm going down, 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 hit the bottom, start going back up again. That's minimal.
What?
Happened at -3. At 2, I had a maximum because the opposite happened. I was going up, 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 then hit 2, so we're going down, down, down again. You can see it on this graph here. I went from negative to positive, then from positive to negative. So minimum, maximum. Okay? Yeah. Questions? All right.
Is that it?
That's the first derivative test. That's all of chapter 3.3, by the way. Yeah, no. They spend an entire chapter explaining basically what I just explained to you in 5 minutes. Okay?
Again, they're just not as good as the teachers do.
It's not very hard stuff. The next thing we're going to look at is something called concavity.
It's easier to destroy than create.
concavity and the second derivative test. Okay? So, concavity is the whole notion of whether the function opens upward or downward. Okay? So basically, concave up, concave down. Okay? If you think of it that way. Alright? So, concavity is how a function opens. Okay? And we have concave up, meaning the function opens upwards. So an example of that might be something like, that's concave up right there. Okay? Concave down, f of x opens downward. So the example, concave up, concave down, okay?
No left and right, just up down.
Huh?
No concave left, concave right. Oh yeah, there wouldn't be a function.
And we don't care about left or right,
Yeah.
basically. Alright, now, what does this have to do with the second derivative? The second derivative can be used as a test to see whether we open upwards or downwards, okay? So, concave up happens when f double prime of x is greater than 0.
What?
So when the second derivative is positive, you're concave up. When the second derivative is less than 0, you're concave down. You open downward. Ah! Isn't that easy?
That's crazy.
That's crazy easy, okay? Although, what's going to happen when the second derivative is equal to 0?
It's a line. Is it just a straight line?
Okay, not quite a straight line. What happens there when the second derivative is equal to 0, you have what's called a point of inflection, okay? And it's the place where concavity changes from up to down or from down to up, okay? It ends up being another type of critical point we can look for, okay? So, when f double prime of x is equal to 0, okay, x is a point of inflection. Okay, POI. Okay? And so what a point of inflection means is the place where it's a critical point where concavity changes from basic, or concavity changes. So it means concavity goes from being up to down or from down to up, okay? So an example of where one would occur, this point right there, that's a POI. Because before it, I was concave down, right? After it, I'm concave up. So it's basically the point where we could stop saying, we could start saying, okay, I'm actually, where I go from opening downward to opening upwards. Okay?
Could you do that anywhere?
You're right, it could be anywhere in there. Okay, and that's why you would actually take it, but it doesn't necessarily fall halfway between. Okay? But somewhere in that zone, there's going to be this point of inflection where this happens. Okay? Alright. Any questions about that there? Guess what?
Are we done?
That was chapter 3.4. That was the second derivative test.
Why is the book so unconcise?
It's, part of it is they're just being very, very thorough. Okay?
Very thorough.
Very thorough. Okay? And so, but basically, you're just, wanting to test these things out. Okay? there's alternate definitions of concavity that you can check. Okay, like for example, concave up means your secant a location that's concave up means that the slopes of your tangent lines go from negative to positive, and concave down means the slope of your tangent lines go from positive to negative. That's another way you can think of it. Okay. There's another version of it that has to do with secant lines, but it's much more complicated. Okay. While keeping it simple with the second derivative test makes life easy. Okay. Any questions? All right. We have a test on Thursday. I will have review sessions tomorrow. Okay. I will post on Canvas when those will be. All right. Have a good afternoon.